Wait a minute, please. Okay, so now we're live. Okay. Okay, Sergey, the floor is yours.
Okay, thank you. And good afternoon or evening or morning, everyone who joined this seminar lectures, which organized by International Association of Pedagogical Sciences and the World Association of Soil and Water Conservation on the case from Moscow State University. And it's a big pleasure. This is their third course for the last 3 years. And the first one was held in 2020 and attracted quite large visibility. And the lectures are available on the same channel that's we plan to also serve this lecture from this course. So this year we plan to have 5 days of the lectures. There's a break on Sunday, and there is 1 or 2 lectures per day are planned. The general title is the modeling of water erosion, hydrologic and geochemical impacts. See, that's maybe a bit louder to talk. Yeah. And so with this first day of the lectures, we will, it's a big pleasure to invite Lizaga with the lecture related to fingerprinting approach. And so we plan that if we have some up to 1 hour timing for the lecture, there can be the questions at the end and some discussion if needed, but I think we will we'll look up at the 1 hour schedule in total. So this is our aim to do this. On the next days, there will be tomorrow the lecture related to the machine learning application from Jing and Zhou from Tongji University from Shanghai, China. And on Saturday, there are 2 lectures. One is from the University of Pavia from Professor Michael Merker related to the modeling of the soil erosion applications, and followed by the lecture from the Vukochaev Soil Institute by Dr. Andrei Zhitkin related to the reconstruction of the soil cover degradation, and with the case studies from Russia in this regard. So we will shift from different also regions in this discussion. Then the Sundays will be the break in the this series, and this Monday will be followed by the Professor Paulo Porta, who is proceeding with another approach on these sediment-related studies with cesium sampling and modeling campaigns. And Paulo Porta is the president of International Commission on Continental Erosion, which is one of the co-organizers of this event. And the second lecture and workshop will be done by Dr. Anatoly Tsiprenko from Moscow State University related to the soil erosion modeling in R. With specific examples and approaches which can be done on that. And the final day, we will have the mix of the online and offline meeting, which will be organized in Lomonosov University, and there will be the lecture in Zoom by Said Sadeghi from Iran related to their approaches on the watershed health assessment. This will be the final lecture in this seminar series. Again, all the lectures will be based on the confirmation of the authors and presenters uploaded into the YouTube channel, and so the registered participants will get the link to follow this at any moment. And on behalf of organizers and follow for the first lecture, I extend you very big greetings and appreciation of the willingness to do these lectures. The international organizers will provide the certificates for the lecturers at the end, and also all those who will join the lectures and registers upon request can also get the certificate of attendance. So for that, please don't hesitate to contact the organizing team. So with these general remarks, it's my very big pleasure to invite the first lecturer in this seminar and first to announce the opening of this lecture series and to wish all to find interesting examples and approaches to this discussion and lectures. So, Ivan, you're very welcome, and good luck, all of you.
Hi, hello everyone. Thank you all for being here, the ones who are here. First of all, I would like to thank Anatoly for the invitation and also for organizing this friendly event to update our knowledge about soil erosion and more specifically today about sediment fingerprinting. Well, in the fewest possible words, I would like, for those that you don't know me, I guess most of you, I'm Ivan Lizaga from Ghent University. I'm a geologist who, after working on geological risks, mostly sinkholes and landslide, and a small period in the private company about landscape and nature preservation, I moved to the exciting world of soil erosion, in which I'm right now. I specialize in soil redistribution rates and dating by using radionuclides, soil nutrient redistribution, remote sensing, and as you can guess by the title of my presentation, in sediment fingerprinting too. I would like to apologize because I could not make the presentation on live. Right now I'm doing fieldwork in DRC, Congo. That's the internet, despite it looks like it's holding it right now. It comes and goes. So I recorded the presentation yesterday night. So also if you heard some words in French mixed with English, sorry for that. That's the reason. I'm talking all these days in different languages. So as I will say during the presentation, any doubt you want to solve about FingerPro, Mixayar, all the different mixing models, the tracer selection, tracing from different nature, etc., do not hesitate to contact me anytime. Of course, these days I'm going to be a little bit busy here, but as soon as possible, I'll reply to you. Thanks for listening. I hope you enjoyed the presentation. Before I forget, I have a lot, well, Anatoly has a lot, the most relevant bibliography I will talk about in a folder together with the links, the most interesting links to the videos. It's an open link, so every time you want, you can just go by and download the PDF of the files, etc. So if Anatoly, if you want to proceed to put the video, just in case my internet goes down.
Yeah, thank you, Ivan. So I have just sent the link to Bibliography Google Drive in the Zoom chat. It is also available in the description of the video on YouTube. So you're all free to take a look on it. So just general remarks. If you have any questions, don't hesitate to ask them either in the Zoom chat or raise your hand in Zoom, or you can write a message in YouTube comments or YouTube chat. So after Ivan's presentation, there will be some minutes to interact and to answer your questions. So we're really looking forward for your feedback, and if you've got any concerns, please write us. So now let me start Ivan's lecture.
Hello everyone, and thanks for being here. First of all, I would like to thank Anatoly for the invitation and also to organize this nice event to update our knowledge about soil erosion and sediment transport. Today, I will try to talk a little bit about the sediment fingerprinting technique, but not only about its advantages, but also about some of its drawbacks in terms of modeling and tracer selection, but especially to track its evolution, how it is at present, and my perspective of how we should move forward to improve our community in the near future. For these reasons, the title of my talk is no more no less than Past, Present, and Future of Sediment Fingerprinting.
I have divided the presentation, as you can see in the slide, also in these three stages. Let's move them to the right, and so let us begin by shortly introducing the basics of the technique and how it was conceived, because not much has changed since then. I think the links are on the webpage, but FYI, you have some tutorials videos about the basics of the technique. One is a little bit more divulgative, and another is way more specific and with code examples for you to follow. So if you want to check them, both of them are in my YouTube channel, and I'm almost sure the links are also in the webpage of the Congress. Moving back to the technique, basically it tries to identify the sediment provenance and estimate each potential source's relative contributions to the mixture to prevent different hazards, as the ones that we can see in the slide, such as reservoir siltation, pollutant transport, desert area increase, etc. The key triangle of the technique is composed by the sources, the mixtures, the tracers, and in the centers we could locate the mixing models. This seems pretty basic and straightforward. Let's go a little bit deeper. Overall, we would have our sources, that are the areas or the potential areas where the sediment is exported, our mixtures, that are no less than the composition of all the sediment exported from our different sources, and what we call tracers, that should be analyzed in both sources and mixtures. The most common use in the bibliography are the elemental compositions, radionuclides, magnetic susceptibility, stable isotopes, and nowadays we are starting to play with the environmental DNA. Putting everything together in a model, the model should give us our result of each potential source's contributions to the mixture we have analyzed. So, well, with this assumption, we could consider the technique as perfectly established and working perfectly. Is that true? Is the technique perfectly established? Well, wait for it. Let's take a deeper look and move to the present. From all different tracers, models, and tracer selection method we use, the truth is that we could obtain different results. To test this assumption, it's as easy as to take most of the database and play a little bit with the different tracer selection methods. Once you run the model with these different tracer selection methods, you will see that you have different results. But which one of those results to believe? Are all of them right? Wrong? The situation is in the middle? Well, this is a question that we will go a little bit deeper in during this presentation. Well, based on the assumption I just did and the results on this slide, you can think that the technique is full of gray zones, and you would be right. Here, I have generalized the path to unmixing that most of the studies follow. We have our data, then depending what we have read, heard of, or learned, we select the tracers on one way or another, or we do not select them at all. Then we introduce them into a model as a black box, we check the box, and obtain some results that we later justify based on our expert knowledge. Through the years I've been using the technique, I realized that most studies do not look inside this black box, most likely because there were no tools for doing it, and also because most models are really complex to understand from a user's perspective. In the end, you cannot be an expert on chemical analysis, fieldwork, cartography, and also programming. Besides, if we look inside, we could see things that we do not like, and mostly we don't know how to explain. Another good reason is the fact that exactly the same procedure has been done in the 100 papers before yours, and it always gets more difficult to publish if you try something different or more complex? Well, in terms of modeling, I have grouped all these concerns in three. The first one, that is the one we already saw. Would it be that different accepted methods in terms of tracer selection give different results? The second one, that different tested models, and I want to emphasize here tested because we already know that they work, also give different results with the same database, depending the tracer selection methods. By combining these two concerns, we already have enough uncertainty to obtain several different results from the same study and the same database. In addition, we have the particle size and organic matter correction factor, but this is a topic for an entirely different presentation, especially because recent research highlight that at least for particle size, you cannot apply an homogeneous correction factor, and this introduces more errors than you are preventing sometimes. This research was recently published by Gaspar et al. Finally, and the most important one, at least from my point of view, in addition to the black boxing, there are some misconceptions considered as true around the technique that make it difficult for users to compare different studies or fully understand the technique. Exaggerating a little, we could assume at this point that the fingerprinting community is blocked or stuck for the reasons I stated before. There are way more papers that are repeating exactly what has been done in the past, or repeating the past with small variations, than the papers that try to openly expose their results and are critiqued for how the technique is implementing or sharing the codes and database. This is happening because most people are users of the technique and they are implementing the state of the art when using the technique or what most people are using at that moment. In order to move forward into a more solid technique, we need to change this trend and either start to be a little bit more concerned on how our models have reached these results, or start increasing the manuscript or research that go deep into the technique and share their codes or data after publishing. For this reason, at present, I do not say that the technique is full of gray zones, but that it's full of opportunities. The technique has been considered as mature for so long that there are a lot of areas where it can be improved. During the last year, there have been some manuscripts starting to wonder how to expose what models were doing and trying to find tools for users to explore inside the box and fully understand what was leading their models to their final results. There are more than the ones I'm going to explore today and explain today, but these are the ones I know the best. Some examples of the method that follow this criteria will be the following. These methods were not developed to provide the users with a definite answer, but to help them understand the model outcomes and especially help them with the tracer selection. All these methods were conceived to prevent the black boxing and help in the understanding of how different methods produce different results. Let's take a deeper look, but a quick look, to the basic concept of these methods. For additional info, I will provide the links to their respective articles in which you can check the equations and a more detailed description of each of these methods. Besides, the codes are all available on GitHub, and also you can run these methods with the code examples that are present in one of the videos. In a nutshell, the CI, for example, extracts all the possible prediction of each single tracer. To see it more clearly, let's take a look to these ternary charts. Each vertex represents the 100% contribution of one of the sources. Thus, every single blue point we can see in the graph represents a possible outcome when combining this tracer with another one for a specific mixture answering the same potential sources. This is one of the most interesting things of the method. It uses the mixture and the sources data in an unmixing environment and plot the possible outcomes. Thus, the user could decide to remove them from the selected tracers or not. Let's take a closer look to how this new info could help us decide and further understand our dataset and the model's outcome. Let's imagine, for example, to unmix three sources, we only need to choose tracers. Let's select, for example, these two, Varion and Strontium. We can see that they cross in a common area from which we could guess a contribution of approximately, let's say, 60, 10, and 30% for these three sources. Now let's introduce these tracers in an unmixing model and see which is the result. Voila! The unmixing model, either frequencies or variation, displayed quite similar results. Following this premise, similar results can be extracted with more tracers. I would like to highlight here, just to clarify, that for the same sources dataset, if we have a different mixture, the prediction will change, because as I said before, this method uses both sources and mixture to obtain the results. Here we can also see the cross of three different tracers and in red the unmixing results. Of course, these things start to get more complex when we have way more tracers that they cross in different points, and this is why we need the unmixing models, and we cannot do this just by viewing the triangles. Also, I would like to highlight that an updated version of this index is about to be released. Well, we saw the method in an artificial mixture that, despite not being perfect as the virtual ones that we can create with our computer, they are pretty straightforward. But how does it look in a real dataset? This CI method. Here we can see the tracers ordered by the degree of conservativeness as the CI ranking is defined. Let's take a look to, for example, these tracers with nice conservativeness index, one with medium low and one with low. And let's take a look of these tracers in Boxplot for clarity. Here we can clearly see why the radio has obtained such a low conservativeness index, because it's totally out of the source's range. On the other hand, a more difficult analysis is needed for the varium, because it's apparently close, the mixture is apparently close to one of the sources. However, most of its possible solutions are out of the physical of conservative space. This is why it's obtained a medium low conservativeness index. One amazing thing also of these methods is that by extracting the patterns of the solutions on each tracers, allow us to group the tracers with similar behavior as the ones in the figures together. As we can see with real dataset is when complex processes such as depletion or enrichment start to happen to our tracers and to our dataset, and it's especially then when the modeling part starts to get interesting. Let's take a look to this artificial dataset. As we can see, most of the tracers are almost perfectly cutting the known solution represented by a black dot in the middle. We know this solution because this dataset was produced in the lab and the mixture created with a known proportion of every source. In this example, the source contributions are equal. For this reason, the black dot is in the middle of the triangle, representing 33.3% contribution of its source. However, despite all tracers are apparently conservative, we can see here highlighting some that are introducing erroneous information to the model, and none of their solution pass through the theoretical solution, represented by this black dot. But that is nice in an artificial sample than this one, because we know the solutions. But how could we identify these erroneous tracers in a real dataset, in a dataset that we do not know the real solution? So for this reason, additional tools are needed to understand what's happening to our samples and which tracers are affected by non-conservative processes. To tackle this problem, the CR method was developed. As the same as with the CI, I'm going to start showing the basics of the method, test it in an artificial dataset, and check how it works and how it affects a real dataset. The basic concept of this new method, as the previous one, is to use the information of the mixture and sources to create rules, but here based on consensus to allow the tracers to debate between them. And yeah, you heard it right, to allow the tracers to debate between them. This is a basic explanation of how it works, but I think it's quite illustrative of the method. For 3 sources, we take these 4 tracers. As we can see, we have multiple solutions. Then we start removing one tracer at a time, and the tracer whose exclusion produces a higher consensus is marked as dissenting and a negative score is given to him. This is how the method is able to create a ranking and to deal, for example, with corrupted or polluted tracers. Of course, this procedure is repeated thousands of times with different iteration and also moving with a different solution of its tracers. But this example is basically the concept of how the method works. Let's go back now to the artificial dataset we were checking before. If we apply the CR or consensus ranking method, we can see how the ranking gave the lowest score to those tracers that are farther from the theoretical solution. If we take a look to the CI index in this small image, we can see how the CR method successfully detects those that apparently are wrong somehow. We need to highlight that this method have no idea where the theoretical solutions are. So they have figured out, the CR method has figured out by itself that those tracers are wrong somehow. But now let's check this CR method, the ranking, in a real dataset. It can be seen that not only promote those tracers that are apparently more conservative, but also correctly classify those that apparently are not conservative. To further check this method, it was decided to unmix the real dataset we have been seeing with a frequentist and a Bayesian model. After both selecting the tracers with the rank test, as we can see here that the outcomes are not equal and also with low defined solutions, and then unmixing those tracers, selecting the tracers based on the CR. The results speaks for themselves. For the first time in the bibliography, both frequentist and Bayesian models show similar results in a real dataset. However, don't stop there. Let's further test the method and see how it responds to polluted or corrupted tracers. To this outcome, we decide to corrupt 2 tracers from the real dataset we have been seeing, which one of them, the phosphorus, passed all previously implemented tracer selection methods such as the rank test, mixing polygon, Kruskal-Wallis, and DFA, while the potassium-14 only passed 2 of them. Both ways of selecting the tracer have been used in the bibliography and they are considered as correct. The graph displays that all previously implemented methods select exactly the same tracers in the original dataset and after the corruption of these 2 tracers. However, when we take a look to the CR method, we can see how it's effectively detected the small corruption of these 2 tracers. Finally, by answering the following questions, the authors discovered the existence of multiple conservative, consensual, and consistent solutions in real datasets. Thus, in order to individually identify all of them, the CTS was developed, that basically search and find all mathematically consistent solutions in the dataset. By extracting these solutions individually, and with the help of the CI and CR method, it was understood why different models had different results when unmixing with the same tracers. However, after selecting the different group of tracers with these methods, both models agree in the results, contrary to what happened when selecting them following the state-of-the-art method, or what was considered the state-of-the-art till now. But why is that method needed? Because we do not like black box model. Imagine if your dataset has multiple solutions and you introduce tracers that pinpoint to some of these different solutions at the same time but it's what happens most of the times when using, for example, the DFA. Your model could choose to go for one of them or just to fall in the middle. But despite this is a huge issue, the major issue here is that you never realize of the existence of the multiple solution or why your model chooses between one or not the other. By knowing them, you can decide based on your expertise which solution make more sense, and also you know that you have different solutions. I would also like to highlight that there are also cases in which all your conservative, consensual, and consistent solutions pinpoint to a similar solution. The advantage of these methods is the knowledge provided to know when this is happening, why, and when it's not. For these reasons, all these methods were developed to be implemented before unmixing and produce comparable results from different models. Well, now that we have explored these two issues, let's move to clarify some misconceptions that are growing around the technique. Here I have displayed some of the biggest ones. The first one is the use of traditional tracer selection method. This should be treated with special care because, as we have seen today and in multiple research, it has been proven that could introduce erroneous tracers to the models without the user knowledge that negatively affect both frequentist and Bayesian models. Thus, being all the described methods, the ones that I have described today, all these tools freely available and with code examples online, if you decide to go traditional anyway, you can always use both and check your datasets and your results, and if you have different consistent solution, erroneous tracers, etc. Do not forget what we have seen here. They can sometimes work, the traditional tracer selection methods, but you cannot be sure if you only use those. The second one answers also the third one. Some models can deal with non-conservative tracers. Well, this one can be easily tested with the following example. Just corrupting one of the tracers in these two sources example, and we can clearly see how both frequentist and Bayesian models are biased by it. The main issue here is that even if you find some models that could deal with some slightly corrupted tracers, the user, once again, will never know if the model was able to do it or if the user has obtained a wrong result. The last one is just to highlight that there are already some methods out there that allow you to unmix stable isotopes with concentration data not only in all unmixing models, but that also allow you to combine them with geochemistry and other scalar variables, and especially now you can implement all the previous methods we have mentioned here in those tracers with concentration data. This can be checked in the original paper, but you also need to know that I have planned to do a video tutorial about this topic too. Well, after summarizing all these misconceptions about the technique, let's summarize where the technique is at present before moving to the future, and how I think or I believe we could move forward and create a better and more open community, higher reproducibility, and make possible the comparison between different study areas. The road so far, tracer selection methods are crucial and could substantially modify the output of the models. Frequentist and Bayesian models agreed when using the CR and CTS methods. It is crucial to avoid the use of a mixing model as a black box. We need to move forward from the traditional implemented method into more informative ones to homogenize the technique and promote its reproducibility and comparability between studies. The CR, CI, and CTS method give researchers the opportunity to apply their expert knowledge out of the models and fully understand their datasets. In my opinion, fieldwork still should be the more important part of every study, together with mapping and the study area understanding. After this, we should keep the black box at home. A nice approach to follow would be to understand our dataset before unmixing, in a way that allows us to understand which effect each tracer is going to produce in our model, or if we have different solutions, display them and state why do we think one has more chances to be the real one. Basically, opening and dissecting the models and our results. Also, it would be nice that everyone would feel free to state the limitation of the implemented methods, including the ones I have presented here. This will help not only the community but also the developer of the methods to improve these results. Now, moving forward to a brighter future, there are also some nice proposals open recently, such as the creation of a common and open access database with tracers from different nature and also from different lithologies, land uses, etc., in which everyone could test their method and also use it as a training database for the development of new methods or different mixing models. This idea was suggested in the 2 tracing days meetings of the last 2 years. The summary of this meeting was recently published as a research paper in Journal of Soil and Sediment, if anyone wants to check it. I will leave a slide with all the bibliography at the end of the presentation. Additionally, this is my opinion, I think we should move to a more modern way of communicating our research, concerns, and doubts. It cannot be that we need to wait until the next conference to establish new network or collaborations. It would be nice to ask part of our doubts publicly. There are a lot of doubts that are shared from the entire community. If we could ask these questions in open platforms such as GitHub, a quicker and a more productive discussion both exists between all fingerprinting users. Of course, this is just a suggestion for general questions about the technique and not a specific one for a specific study. Finally, I would like to highlight the new alternatives when publishing, such as preprints, and also, as I have proposed in previous talk, the creation of an open forum to discuss recent developments of the technique, without the need of waiting till it's fully published. If you find something that could affect or interest the whole community in this type of forum, it could be served. I'm almost finishing my talk, at least the part about modeling, and following the last statement about create a different way of communicating and more open, I would like to share a small piece of the results of our recent research we are doing right now. We have been detecting strange behaviors in the models when working with really high or low contribution in both the model we have developed, FingerPro, and the others we are using constantly, such as Lizaga. Thus, finally, we have decided to go for it and further check this strange behavior. To generalize and exemplify our finding, I'm going to use a virtual mixture of 4 sources as example. I'm using here a virtual mixture because the fact that it has been created virtually in a computer prevents the errors in the models of removing any non-conservative behavior from nature. Thus, the result of all models should be perfect or close to be perfect, as we have been seeing in several studies. However, this is not totally true when dealing with high and low contributions in sources with medium or high variability. Let's see this in an example using both Lizaga and FingerPro. Here we can see how both models introduce medium to high errors for a virtual mixture where the error should be close to 0. That could make us wonder that if we have such a high error in a controlled environment, how big this error could it be in real dataset, and furthermore, how we could check it. For this reason, we decided to introduce a new method in the FingerPro package to prevent this mathematical error. I would like to highlight that the error is directly linked with the model and not with the database. This is why we use virtual mixtures and virtual databases in this research, to be sure that we were only analyzing model issues and not issues related with the data. As you can see in the next image, after implementing the new method in the FingerPro model. This one fits the theoretical solution almost perfectly, what was expected with every model when working with virtual mixtures. Well, some general remarks I would like to share with all of you about the upcoming research is what we already saw, that the old models produce errors for high or low contribution sources with medium to high variability. That the upgraded FingerPro deal with this problem. Also, I would like to highlight that this method will be included in the FingerPro as a Boolean so that the users could decide to include the new method or not to check if their results were containing that error. And also, for example, users for another model such as Lizaga that could also check through FingerPro if they have been affected by that error. Extra information that will be available in the upcoming paper: the origin of the problem, explain does it affect all models, how was solved in the FingerPro, and some tips, as I explained, to detect it when not using the FingerPro model. Well, regarding the part of modeling, so that will be all from my side. Thanks a lot for your attention. I hope it was not a lot to process for one talk. Anyway, if someone has any doubt, concern, or need help running either Lizaga or FingerPro, do not hesitate to contact me. I will be super happy to help. Besides, if you follow the FingerPro repository on GitHub, you will see that it's monthly updated with more optimized code or methods. You can post your questions there, or if you think or something that could be useful to include in the model, either for you or the community, let me know. Here we can see an example of one of these suggestions. The guy was asking to include the ID of the samples in the LDA plot. So the same day I included a boolean in the function to let the user display this number in the LDA plot if they want it. Thanks a lot for your attention, and do not forget to visit the repository and the tutorial videos. If you do not have access to YouTube, the videos are also available in Bilbliography, which is a Chinese platform. Thanks again.
Okay, so Ivan, are you here?
Yes, I am.
Yeah, thank you very much. I really enjoyed your talk. It was really nice. So, have anybody has any questions? Don't hesitate to write them in the chat or question and answer box.
Hi, can you hear me?
Yes, please, Alonso.
Yes, thank you for the presentation. It was so good. They developed the package to do that. Here in Peru, I work with soil, and also I work with mining sometimes, and now in landslide rigs. And I work a lot with water, sediment supply and things like rocks, not geochemical. So I don't know if the model or the thing, because recently I'm knowing this, I don't know that exists, FingerPro, works with non-detect data or the data below detection limit, because some elements that I have a lot of below the detection limit, values that they are significant amount, sometimes 30%, 40%, 50% of the elements are below the detection limit. And in water, when I create models, I work with, I don't know, the package NADA package, and also with survival analysis. So I don't know if this model or this package can deal with non-detect data analysis, like data below the detection. That's my question.
Okay, thanks a lot, Alonso, for your questions. Yes, we have also deal with these issues, but just when we have like a small amount of elements that are below detection limits. I cannot give you an exact answer, but yeah, you can try and check if the CR, for example, can really deal with which one is more conservative or which one is less conservative, because there are a lot of approaches also to fill the holes in your database. Like for sure you have tried like the machine learning, and I think the NADA package also fill this hole in some of the same way. But yeah, without trying, I cannot give you a exact answer because yeah, we only deal with a few elements below detection limit, but I guess you are asking about a whole database full of below detection limit data. Is that right?
Yeah, because I have a huge amount of data. Normally I work with, I don't know, 300 variables that we have to deal with all the chemical mixture, and also to because I work in three things different, because that's the soil supply is important to me for like the catchment areas. When it's the accumulation of sediment, it's important to sample that places, and on the river also when it's not when to take the sample, that's important for us. And also that means that I don't know how to explain that, but I analyze each element and all together how it's work. No, I don't know too much into sediment modeling, but I entered this to learn. No, but it's only a question. Don't worry about it. I'm going to test and then learn more reading the finger
Oh
pro
yeah,
package, because I don't know too much.
yeah. If you have any doubt, you can just email me with that doubt. Or what a lot of people do when they have doubts is send me like their database, but without the IDs and the headings, and just invent and put names or different things just to check how the things could work, or just they send me a portion of the database, and I can do a code, or we can check, or you can check yourself and ask me questions after, as you please.
Okay, thank you so much. Thank you.
Okay, thank you, Alonso. By the way, can you please write the name of the package in the chat? Because I'm really interested in to try this package for my data. However, Ivan, I have one question to you. Did you try to compare FingerPro results with another frequency models like SIFT model from Simon Pooley and Adrian Collins?
Yeah, we have compared. There is I think it's an abstract of the EGU in which like we try 4 of the models, but we have not published anything yet, like comparing more models, because suppose that the frequencies models works in a way, and we were more concerned on dealing between the frequencies and the variations. But yeah, I think it could be interesting to just compare all the models that are out there. But the thing that we have found every time we try with different models is that the tracer selection is what changes the results. So probably is FingerPro and Lizaga agree in the results once you correctly select the tracers. Probably the rest of the models should do the same.
Okay. Yeah,
yeah, I think it's quite interesting to do it, and also to check how the other model works.
Okay. Thank you. And is there any questions more from you guys?
I have a very stupid question, because I understand that for you it's evident. I don't use these programs, and no, I don't investigate sediments. So, but why these methods of fingerprinting, sediment fingerprinting, use 3 sources at a time and not 4 or 5 sources at a time? Maybe you can explain me. It's in a simple way. All your triangles you were with of 3 sources, yes, for each element. I don't understand this methodology. I should read further, but maybe you can explain me this. Why 3 sources?
Yeah, that's the thing is that with the triangle, it's pretty easy to explain the methods, but all these methods are developed for the number of sources you want. I mean, in the manuscript of the consensus, or in the one they combine with CSSI, you can see the triangles for 4 sources. The thing is, when you go from 3 sources to 4, you add a dimension. So you need 6 triangles from the same tracer to visualize. But if you move from 4 to 5 dimensions from the 5 tracers, no, sorry, 5 sources, then it's impossible to visualize. At least you do like a simplex or something like that to homogenize and put the data together. I just use the triangles because it's the easiest way to understand and to see the methods. But you can apply the CR for 4, 5, and 6 sources, and also the CI and the CPS.
Okay, so multidimensional vector. Thank you. Yeah.
Okay, thank you. By the way, if any more, Ivan, can you please give give the name of the new method you introduced in the end of the lecture? So you gave us an abbreviation of LVP, but I didn't saw the transcription.
Yeah, I didn't add the transcription.
Okay.
that's true, because yeah, we are still going up and there, and it's changing from time to time. But yeah, I can give you. I think it's not in the, maybe in the folder. I put it, but I'm gonna check if not, yeah, it's.
Yeah, because honestly, I was really impressed by the difference of virtual mixture and mixing. Yeah.
Yeah, it's the linear variability propagation method.
Okay, thank you very much.
I wanted to check to be sure.
Okay. Okay.
Okay, one more question.
No, yeah, but we
Yes,
were really
please.
surprised about that, because yeah, it was true with virtual mixtures that usually when we try that, all the models fits almost perfectly. But now we were trying this pattern I have been seeing all since I started my PhD, like when you have high variability in your sources, that like Mixire, for example, try to move to the center the sources. There is no super high contributions. And also we saw the same to FingerPro. And at one point we say, okay, let's take virtual databases from here and here to check it. And we were surprised with the results. I mean, I just saw one of them. It's not always that bad. If you don't have this high variability in the sources, for example, the results are quite similar to FingerPro and Mixire, but that's the problem. The user don't know. Sometimes you put it there and you say, okay, yeah, that's okay, nice. But then even with virtual mixer, you say, whoa, the error is higher than the 50% in some of the sources.
Yeah, it's really nice, interesting. So Nikolai, please.
Yeah. One more question. So here, these methods, you use chemical elements as tracers for detect sources of sediment, as far as I understand. So the attitude is like that all elements are tracers for sediments. Is it possible to use these techniques to detect sources of chemical elements themselves?
Yeah, I guess you can use it, but the thing, for example, there are like some patterns we follow in the fingerprinting, but of course everything can be allowed. That, for example, the traces we use, we think or we suppose that they are totally conservative. This is why all these different tracer selection methods produce different outcomes. That means that the tracer, when it's eroded from, let's say, from the forest, one tracer is going to reach the mixture without being altered. That is something that is really weird to happen in nature, but this is why we use all these tracer selection methods to prevent that. And answering to your questions, I think you can also use that. But yeah, I would need to look how to adapt it, but for sure.
But they are for conservative elements only here for now. So if if it's a little unconservativeness, so it's impossible to use these methods that you mentioned.
Well, no, it's not at all. I mean, it's for real 100% conservative. I don't think there is any element in nature, especially the geochemical elements. But if the conservativeness is quite close to not 100%, but the tracer is really conservative, you can use it anyway. But this is why all these methods are getting more and more complex to prevent that you put a tracer that is totally biased and giving you different results or that a tracer that is totally polluted just give you a different result. But it's because the tracer is polluted and the tracer has not reached from the source to the mixture intact.
Okay, thank you.
Okay, thank you, Ivan, and thank you, Nikolai. So, if there are any more questions, you're welcome. Okay, yeah, thank you for your comments. Yeah, so I think let me finish our discussion for today. Thank you very much, Ivan, for giving us this talk, and thank you very much for all of you for your questions and for participating. I really like that we have so active discussion, I think. I'm really looking forward for your I'm really looking forward for your new updates of the package. I'm the stargazer on your GitHub, and if I can help with developing your package, I would be really glad to join. So, okay, so thank you very much. See you tomorrow. We will have a lecture by Dr. Zhu on 3 p.m. Moscow time about extreme rainfall analysis. I guess it will be really interesting also. So thank you very much and bye.
Thanks. See ya.